Good evening and welcome to episode 3, season 3 of the Late Night Conference. My name is Wilhelm Huck and I'm your host tonight. Thank you so much for joining the Huygens building. Also thank you when you're watching online via YouTube. It's my great pleasure to continue this series on chemistry and AI, because I think AI, when we are going to implement it fully in chemistry, it's really going to radically change the way we do chemistry or make chemical discoveries. And this can be in medicine, drug discovery, but also in all those areas around us where we have formulated different products. And I think eventually it will really change the way industry, where you could think of changing formulation from an art into a science-based technology. Now, in the first 2 episodes, we introduced AI in different forms a little bit, getting you familiar with the basics of how you sort of think about molecules and introduce them into AI algorithms. We discussed diffusive AI and sort of modern developments. But today we're going to really take it a step further and really sort of going to look at how AI can be used to predict reaction outcomes, to predict yields of organic synthesis, and really also build up complete synthetic routes aided by AI algorithms. And today's speaker is really one of the leaders in the field who started implementing AI in a very early stage in his career, already during his PhD. It's my great pleasure to introduce Professor Coley tonight, Department of Chemical Engineering at MIT, and also at the Department of Electrical Engineering and Computing Science. Connor did his bachelor in chemical engineering at Caltech, and then after a master's, he did his PhD in 2019 from Department of Chemical Engineering at MIT. So indeed, he looks young, but he is also very young. So he did tell me he did do a very brief postdoc at the Broad Institute, diverting to chemical biology a little. The Department of Chemical Engineering. He has been extremely successful, even though he has been there only, well, 4-ish years, 3 or 4 years actually. He is one of the talented 12 of Chemical Engineering News. Forbes put him on the list of 30 under 30. He's a Dreyfus Scholar. He won an NSF Career Award. There's already too many awards. So let's not discuss the awards. Connor, the floor is yours, and we're really looking forward to your talk. Before I give you the Zoom, for those of you watching online, please put your questions in the chat, and we'll pick them up after the presentation. And of course, in the audience, there's plenty of questions. So Connor, the Zoom is yours.
Terrific. Well, thanks very much for allowing me to join this wonderful program and to sort of present for you in episode 3 of this series. My name is Connor. I've been at MIT for just in my 3rd year now as an assistant professor. And what I'll talk about today are sort of different kinds of approaches using AI for chemistry and for molecular design and molecular discovery. And I'll briefly start off initially just by talking a little bit about my path towards these fields and the different types of experiences that I sort of had in my training. It was not a very direct path necessarily to these topics. So in my undergraduate, my bachelor's studies, I didn't really know what I wanted to do. I was formally trained in chemical engineering, taking chemical engineering courses, but still trying to figure out what the right research area was for me, what I was really drawn to. So from sort of my first year as a bachelor student, sort of working in structural biology, moving into process engineering, trying out internships, trying out many different types of research from experimental to computational, and really just trying to look for what motivated me the most and helped me address some of the most challenging problems. In my graduate studies then, that's when I started moving more into this direction of AI as well as automation. So initially, what this meant was thinking about microfluidic reactors to do sort of reaction engineering and medicinal chemistry, trying to optimize those chemical reactions with algorithms and statistics, some additional research days and visits, including at Novartis, and then really partway through my PhD that's branched into a lot of work in the realm of computer-aided retrosynthesis. And now starting to think about, well, how do we use data, sort of large data sets and historical data sets to help us in the lab? Now, as was mentioned, sort of prior to starting this position, I did also do a postdoc at the Broad Institute. I'm sort of looking a little bit more into chemical biology and trying to learn more about applications closer to drug discovery and more translational sciences. And that was somewhat abruptly cut short then because of COVID. And then, just a few months into the COVID pandemic, I started my independent career now here at MIT. And so even though all of these different topics on the slide sort of cover different emphases, I think the shared sort of commonality across them, the common thread, is that I really am driven by questions of efficiency, of automation, and sort of trying to connect that together with molecular level understanding. And so thinking about sort of all of these different forays into process engineering and optimization, it's really about trying to do things efficiently, trying to run the best reactions, trying to perform the experiments that will give us the most information and figuring out what that means in the context of sort of big data sets in the lab. And so now in the group, a lot of the context for the work that we do focuses around small organic structures and thinking about the kinds of molecules and the kinds of structures that make up the majority of our medicines. We also use these kinds of molecules in many different fields like agriculture and material science. They have very far-reaching properties and some very good advantages as far as sort of their small organic structure can make them sort of easier or cheaper to manufacture than some larger, sort of more biologic or protein-based structures. And they nevertheless exhibit a very wide range of properties. And so what really interests me in thinking about these different goals of discovering small molecules is trying to understand more about the process, right? The process by which we arrive at these, right? So how do we find a new drug, right? How do we find a new dye for a dye-sensitized solar cell, right? It's this process of trying to identify and optimize and ultimately manufacture these different molecular structures, these different compounds. So we often will think about molecular discovery in this iterative way. We'll go through these design cycles, you might call them, where we're going to propose molecular structures, we're going to make them, we're going to test them, and then perhaps after we've tested them, we decide that we're not quite there yet. So we haven't found a molecule that has the right properties, and so we need to use that to then revise our design. And sort of on the context for all of this too is, we apply our understanding to define the goal and say what properties we want to achieve, whether that's the efficiency of a new ligand or the bioactivity of a new drug. And we also try to bring in external information when possible to sort of jumpstart or accelerate this process. And so one of the sort of big themes of the research that we do and the questions we try to ask is that we're trying to build towards this notion of autonomous laboratories or self-driving laboratories, as many people call them, by using algorithms to help us make decisions as we navigate this cycle. So we're trying to make decisions at each of these stages, not based on intuition and years of experience, but based on objective and quantifiable decisions about sort of what is the best action to take at any given time. And so a few of the areas where AI really comes in and helps sort of unlock the potential to, again, accelerate and systematize this process of molecular discovery are in a few areas. So one is in the modeling section. So, a lot of the models that we build, and I'll touch on this, try to understand the relationship between molecular structure and function. And so the model is sort of trying to sort of fill in this question of, okay, well, if the structure looks like this, what might the property look like? That, of course, informs the design. We're in the design stage, we're really making these decisions about what molecular structures are worth making. And then a crucial stage where I've spent a lot of my career is then on synthesis. So in the synthesis stage, right, we have to take this idea, which could be, a drawing on a whiteboard or a structure on a computer, and understand what will it take to actually take this into the laboratory. And so we need to plan the recipe, and we also need to actually run the reaction. And that's why this is a little robotic sort of schematic, because we can also think about laboratory automation as helping us in this process. And so in this talk, I'll try to briefly go through a few of these few different considerations and talk a little bit about the technologies that are being used by us and others to overall facilitate this process of chemical discovery. And so I'll start with this figure, which is adapted from, I think, the same figure that Robert Pulice showed in his presentation as well in this series, where we're thinking about the different ways of defining a chemical space. So I like to think about search and optimization. And so I think about the process of finding a new molecule as the process of searching a large chemical space of hypothetical structures. And one of the ways that we can do that search is by first defining the list of molecules we want to consider. We can say, okay, here's the list of 100, 1,000, a million, 1 billion molecules that I want to look through. And my goal is to find the best molecule from that list. There's other paradigms of increasing interest in generative design, where instead of sort of taking the list of molecules and trying to map them onto function or predict their properties to select the best one, we instead try to take our understanding of the relationship between structure and function and flip it and say, well, okay, if I believe that I can map structure to function, what if I look for the structure that has the best property profile? And so we have this notion that we can invent new molecules, right? The same way that some image generative models like Clip, Dolly, Stable Diffusion invents images given some text prompt. The same way that ChatGPT generates text when given a text prompt, we can also train generative models, but in this case, they're going to be generating molecules, not just images and not sort of natural language English responses. And so even though we're going to start around the design aspects, this question of chemical synthesis sort of underpins what we do here. And the reason is because synthesis and our knowledge about chemical reactivity constrains what we're able to search when we search these chemical spaces. So when I think about these virtual libraries, we can map out billions of structures that we think are synthetically accessible, and we can order them online. We can ask our scientists to help make them. The way that we define and map out those spaces typically relies on what are known as make-on-demand libraries. These make-on-demand libraries are constructed by taking molecules and building blocks that we have on our shelves and chemical transformations that we believe are robust, that we know how to run. And we will virtually simulate what products can we make if we're willing to run one chemical reaction, all combinations of the building blocks that we have access to. And then what happens if we're willing to run 2 steps or 3 steps? And so we have this way of mapping out these very large enumerated spaces that we believe we can synthesize. That helps make sure that any molecule that we select, then we can actually go into the lab and make it, hopefully with some ease. For generative models, this is a little bit more interesting because generative design, right, is a little bit less constrained. Typically, we have these models, these AI algorithms that propose new structures, and we don't have guarantees about those structures. And so sometimes we get molecules that look quite reasonable to a chemist, like the ones at the top. And sometimes we get molecules that look quite unreasonable to a chemist, like the ones towards the bottom. And so generative models can be exceptionally creative, but that creativity comes at a price of whether the structures look reasonable or not is not something that is guaranteed in advance. Now, in both cases, right, our ability to navigate this search space of hypothetical molecules relies very much on our ability to predict what's good and bad. And so when I say good and bad, it will really depend on what we're trying to design a molecule for. And for a drug, we might design a set of properties, including bioactivity, toxicity, solubility, right? A whole range of properties of interest to us. We'll try to understand how modifications to the structure can improve those property profiles. And so what we've been doing for decades and decades in this field is we've been taking the molecules that we're worried about. We've been representing them in this numerical way by describing aspects of the molecular structure or features that we can compute of that molecule. We've been building different types of relationships that then map that numerical vector to properties. And so with increasing interest in machine learning, of course, this is a great opportunity for machine learning because we're mapping a vector or a list of numbers to another number or to a class. And so we can be very clever about what we do for this particular supervised learning problem. Now, one of the big opportunities that's really emerged in more recent years, right, is the use of AI and the use of machine learning models to not just go from this description to the properties we care about, but learn directly from the structure of a molecule. So in principle, if we use the upper approach, there could be an information bottleneck where that initial step of translating a structure into a vector lost some important aspect of the molecule that's really important to anticipate its function. So in the bottom case, if we show our models the full structure, in principle, they can learn more, right? They have a better chance at learning something complex that maybe is not captured by the types of features and descriptors that we were already thinking about. Now, there's a lot of different ways of doing this. And again, I think Robert Pleach's talk was terrific in that it introduced a lot of these notions of graphs and smile strings, right? These different ways of capturing molecular structure in different representations. When we think about AI at a practical lower level, AI for property prediction relies very much on these questions of representation. A molecule is this sort of abstract thing, right? It's this sort of floppy three-dimensional structure that exists in space. It moves with time, depends on the temperature, how much it wiggles around. And there's a lot of complexity in how we capture a molecular structure. And even these sort of typical drawings of these line diagrams that we are used to as chemists, they really emphasize covalent bonds between atoms, but there's other types of ways for there to be interactions between atoms. There's other complexities to worry about. And so I'm not going to dwell on this too much, but there's a whole zoo of choices when it comes to selecting a molecule's representation and choosing what kind of machine learning model it's best suited for. But instead of talking through the details of these methods, I'll just highlight one of the things that these models let us do, which is leverage our computational tools and simulations from sort of small scale to very, very large scale. So we're looking here at a schematic showing docking. Docking is a simulation which very coarsely tries to estimate the affinity between a small organic molecule or a potential ligand and a protein of interest, maybe a protein target that we're trying to bind because it's implicated in some disease. And traditionally, right, what we do in this sort of structure-based drug design world is we'll evaluate hundreds of millions, sometimes billions of hypothetical molecules to try to understand which ones have the best properties. But we don't have to do that, right? Because most of the molecules that we evaluate will end up being relatively poor performing. And so, for example, here, what we can do is we can say, okay, I want to understand which of my 100 million molecules is the best one for this application. But instead of evaluating all of them, I'll evaluate some of them. I will train a model, and I will use that model to tell me which parts of chemical space look better or worse. And we use this trained model as a sort of compass to tell us where we should be looking. By doing that, right, it helps steer us away from the types of structures that don't have good properties and aren't going to help us. And so what we find is that if we're looking at our ability to find really good compounds as a function of how many simulations we're actually running, we can get this really large enrichment where we're only running 1/40th approximately of the simulations, but we're still finding 90% of the best molecules because we've used this model that understands the relationship between structure and properties to steer us and to tell us where to look and where not to look. So we're going to turn now to the generative side, because this is an area where there's a lot of interest in the use of AI. Again, because we can have models in principle exhibit a high degree of creativity. And so for generative models, typically what we do is we will take a database of molecular structures and we'll train this generator to learn how to compose new structures, maybe by piecing together atoms and bonds or fragments, or using that language of smile strings where we can represent molecular structures as text. It will make these new molecules and invent them from scratch. We can then use an evaluator to say whether it looks like it has good properties or bad properties, and that evaluator, again, is going to steer the model so it's more likely to propose molecules with good properties. And so this animation has been showing the result of applying this technique to the design of a PROTAC, which is a particular modality used for protein, targeted protein degradation. What we're seeing here is the generation, sort of atom by atom, bit by bit, of a molecular structure. It's never been reported before, it's never been used before, it's never been synthesized before. It's been dreamt up by this machine learning model trying to find a structure that is predicted to have good degradation performance in this case. Now, the challenge, right, that we've already sort of covered briefly is that sometimes when we have these models be really creative, they can be too creative and they can take too many liberties with respect to the kinds of molecules they propose. And they give us these structures which we can't make. They don't make much sense. They make sense to a computer, but they don't really make sense to a chemist. And there's no way that we even try to synthesize these couple in the lab. And so this is, again, where synthesis really comes in and becomes highly relevant to this question of chemical discovery. Because when we think about making new molecules, we have to have new recipes, right? These recipes being synthetic routes that define the series of transformations that can connect purchasable or commercially available starting materials to the structure that we want to achieve, the structure that we want to make. And so here on this slide, I'm showing an example route. This was a new drug approval several years ago. And so what we can see is that the starting materials in red are connected through these intermediates in yellow through a series of chemical reaction steps that build up complexity over time to get to that final molecule. Now, in organic chemistry courses, right, the way that we're taught to approach the synthesis of new structures that we want to make is through retrosynthetic analysis, just meaning that we work backwards. Right, so we start with the target compound, and we make simplifying disconnections or transformations to simplify the structure until we reach starting materials that we can purchase or that we know how to make. And so humans do this process of retrosynthesis. Again, it's what's taught in our courses. But we've also been developing algorithms to do this since the late 1950s. Right, so almost since the notion was formalized as retrosynthesis, we've had some ideas for computational assistance in using algorithms to help us perform this task. So a very intuitive approach, and the original approaches that were taken were to essentially write down the rules of chemistry, trying to capture what kinds of changes from A to B and B to A are possible, right? And what reactions do you know about? And you can look at these sort of encyclopedia-esque textbooks of named reactions and strategic transformations and start to encode these kinds of patterns. You want to teach your algorithm about the moves that are allowed, right? Unlike other applications of AI to gameplay like chess and Go, we don't have a rule book already written. We don't have rigid rules of, oh yes, this transformation is absolutely possible or this transformation isn't possible. All we have are our best understanding of the types of molecules for which one transformation may or may not work. So this is sort of an imperfect process then of encoding these rules. We don't have the same rigidity as we do in gameplay. Now, the type of approaches that we've been taking, instead of having human experts write down the rules, we've been trying to see if we can learn them. So we've been trying to take these data sets of published chemical reactions and try to infer chemical reactivity patterns and understand what transformations are possible or not possible. Because every one of these entries, there are maybe millions and tens of millions of these, tells us the results of one chemist's experiment, team of chemists experiment. They tell us what reactants or starting materials were used. They tell us what the major product recorded was, maybe the yields of how much was formed, what kinds of conditions were used to achieve it, as well as who did this reaction or who published this reaction. And so it's with this information that we start to train models, right? AI models that can go from products to reactants and do retrosynthesis. They can go from reactants to products and predict the outcomes of chemical reactions. It's all based on this kind of information. This is experimental record of what happened, sort of accumulated over years and years of collective chemistry expertise in the literature. There's a lot of detail that we could go into about what information the databases have, what they don't have, right? The data that we have access to constrains and somewhat limits the types of models we can build. But even though these aren't perfect resources, they still teach us a lot about what transformations are possible. And so we still spend a lot of time building models to do these. So one of the core things that we worry about for designing recipes is retrosynthesis. Again, retrosynthesis is just going to be the task of taking a product molecule as input and outputting one or more reactant molecules. And sort of with this well-defined input-output relationship and a lot of labeled data about what reactants were used to make what products, this is a wonderful candidate for machine learning. Because a lot of what machine learning models can do is learn these complex mappings from inputs to outputs, in this case, from products to reactants. And so there's a number of approaches that have been developed over the years, and I'll highlight also Marwin Segler and Mark Waller as major players in this space, trying to understand the best way to propose these reactant molecules and to do this task of retrosynthesis. And so the exact techniques here aren't so important. What is important is just the fact that because we do have information from chemists about these reactions that were published and performed, we can train our models to take molecular structures as input and output molecular structures that are the result of the transformation. And so with this ability, we stitch these together into these multi-step planning tools, and we can now propose full recipes. So we can take a product that we want to make, and we can say, well, how do I make this product? What is one simplifying retrosynthetic disconnection? And we get one step back. Then once we realize that these reactants maybe can't be purchased or we don't have them in stock, we go one more step back, etc. Until we find a full pathway that terminates in these really inexpensive, viable starting materials. And again, there's complexity in how we can do this search. There's complexity in how we navigate this large space of options. But the basic idea is just that we use algorithms to help us make these simplifying disconnections and connect back to simple starting materials. Now, I described this as a recipe, and that's sort of at some level true. But to be very candid, the level of detail of the recipes that we need goes further beyond what these models are doing right now. So if you sort of have a chemist that goes into the lab, and we think about the role of AI as, again, decision-making help, that chemist has to make a lot of choices, not just about what starting materials to use, but about the conditions, the concentrations. Do they need to put the flask in the oven before they run the reaction? Should they use a flask? Should they use a plate? Should they use a vial? How long should they run the reaction for? How do they purify it or analyze it? Or there's a lot more that goes into the process of chemical synthesis than what is captured by this kind of pathway that we just looked at. And so we can think about this task of synthesis planning and recipe planning as not just retrosynthetic analysis, which would be this first step, but these additional stages of layering in more and more detail. And so as this bullet states, right, chemists, maybe are still happy getting these recommendations of pathways because they can fill in the detail. They know based on the kind of transformation, sort of what conditions should be tried and what's reasonable based on their intuition. But when we start thinking about automated laboratories and autonomous laboratories, we don't have that privilege of getting away with lower specificity. We have to say exactly what we want our robotic platform to do for us. And this is sort of building together AI, automation, and computation, all to support chemical discovery and addressing this bottleneck of synthesis. There's been a little bit of progress in this space. And so I'll highlight this work from Hanyu Gao, where he sort of recognized that if you take a model for predicting reaction conditions, we can actually train it using the information we already have. So if we're trying to say, I want to make product A using starting materials B and C, we can take the data that we have for how A was made from the starting materials, and we can mask the conditions, and we can ask the model to predict those. And so again, when we have the right data for these tasks, we can use AI, and we can use supervised machine learning to fill this in. Right? So there's a lot of tasks like this. We're given the right data set, we can build these tools that are able to make recommendations for us. Now, this and other tools, including the retrosynthetic analysis, are packaged into a software suite that we have been developing and maintaining called ASCOS. So ASCO sort of started several years back under a DARPA, or Defense Department's grants here at MIT. It's been supported by now a consortium of pharmaceutical and chemical companies called MLPDS. And we're continuing to develop it to help with all of these tasks around planning reaction pathways, predicting reaction products, predicting impurity formation, or all of these sort of additional challenges that one has to encounter in chemistry. We're trying to sort of make ASCOS this one-stop shop for a lot of these capabilities. And for this audience, I'll just mention that we're planning and working on a large new open source release by the end of this year. So hopefully there'll be more good things coming. Because what our main goal is, right, in developing and advancing these tools is to support synthesis and to make all of the decisions we need to make to run complex chemical reactions and chemical processes. And so our ultimate idea, right, the ultimate vision is to try to have these autonomous platforms that seamlessly flow from planning to execution, right, combining software and hardware. Because ASCOS and these similar tools I've talked about will help us plan out what we want to run, but then we also have to run it, right? And again, there's a role for robotics, there's a role for sort of autonomous laboratory platforms in executing what our planning algorithms suggest we should do. Right? If we propose a molecule, we should be able to make it with minimal human intervention. Right now, that's not fully possible. There's a lot of work in automated laboratories in chemistry over the years, but what I would say is almost uniformly true is that when they're trying to make a new molecule that hasn't been made before and that combines, a number of different types of chemical reactions, they still need some help with the planning step. And so when we think about the role of AI in chemistry and the role of AI in chemical discovery, there's all of this work in the hardware side of automated labs, but there's only been partial work in the planning and software side for these automated labs. And so we can plan parts of the recipe and parts of the route, but we can't plan everything, unfortunately, yet. Now, one of the sort of longer term investments that we're making into our ability to do this for the field is an effort called the Open Reaction Database, where we're sort of trying to address the fact that in chemistry, most of how we communicate the results of chemical reactions is through text, right? Prose in supporting information documents and manuscripts. But reactions can be provided much more structure than that. And so the Open Reaction Database defines this data model or data schema for organic transformations and provides a database where that kind of information can be stored, retrieved, and we can use it to build machine learning models that understand the subtleties of reactions that current models unfortunately cannot. And so with that, I'll just thank all of the folks who've had their hands in this work, the current group members shown on the left, current funding sources shown up top, present past members of the MLPDS consortium as well. And thank you again for the invitation to join. I'm looking forward to the discussion, and I'll just rest on back this summary slide on the overall vision for how we might accelerate chemical discovery with AI. So thank you very much.
Anna, thank you. Anna, great presentation, and I really like you put this slide up again because I think it really nicely summarizes. You started with the dream of having a self-driving lab, and then you explained how AI, and especially generative AI, can lead to new molecules and how you still have to somehow tame that beast, right? Because otherwise it makes molecules that don't make any sense to anybody. But I think you also then showed the challenges that you have to sort of use it for constructing a synthetic pathway and eventually to go back to your self-driving lab and combine it with hardware. So I have lots of questions because it was a very inspiring talk. There are people in the audience who can ask questions and probably in the chat. But let me start with one comment maybe to kick off discussions. My driving license, because by that stage the self-driving car would have arrived, and who needs a driving license if the car does all the driving? And that was, well, not too long ago, but it's still about 7-8 years ago. And I was wondering, this self-driving lab that we're trying to build, how close are we? Is this Is this something that is going to be another 5 years forever, or is it something that you really see appearing in a relatively short time frame?
Yeah, that's a great question. So when I think about sort of self-driving labs and how the field is evolving and its capabilities, I will say, first of all, things are moving very quickly, right? There's a lot more interest and investment into this space, especially if you look at sort of cloud laboratories that are becoming very popular and very robust for the automated biology experiments. There's a lot of interest in extending that to chemistry as well. But I think about sort of the automated lab capabilities in terms of the scope of problems they help us address. And so when it comes to chemistry and chemical synthesis, as one hypothetical, suppose that you wanted to make an automated laboratory to run chemical reactions, but you were focused only on amide couplings, and you were focused only on building blocks that were natural amino acids. We have that, right? We have automated peptide synthesizers that are very robust and operating within that space. So then we can think about how do we take that scope, right, which again is very robust. Self-driving labs, you could use that to refer to the synthesis of peptides if you wanted to, and think about the generality of it. And so, certainly there's always going to be capabilities that are being added to these automated labs for chemistry, improving their ability to run certain types of transformations that are more difficult procedurally. But the basics of combining reagents, heating them, analyzing what happens if you can get everything solution phase, those are the kinds of workflows that are becoming very, very robust. But again, I don't think the physical operations of mixing liquids and heating them, if we're willing to say for a limited scope of chemistries, that's all you have to worry about. That's not the heavy lifting that chemists do, of course. And so there'll be a lot more challenges, I think, still, even as these evolve over the next couple of years. I can no longer hear you, sorry.
It's back on again. I think you mentioned in your talk already the requirement for teaching the AI not only the transformation of one molecule into the other molecule, but also the reaction conditions and how to, in a way, using supervised learning to let the AI already come up with ideal conditions, because that's what you definitely need in the self-driving lab. One thing that you didn't mention is, can we use the AI to really make molecules in 100% yield? Because otherwise you always have the purification where you, after every step, you have to purify them. And that seems to be, well, that could be a real bottleneck.
Yeah, no, that's absolutely right. So one of the things that I'll mention is I think that while we try to get the reaction, we hope to get the reaction conditions, quote, perfect on the first try, I wouldn't say it's a necessity. And so if we think about the overall framework as I presented here, it's a rather linear pathway of, well, let's get the pathway, let's get the conditions, and let's sort of move on to run it. But in reality, these types of platforms can have some sort of feedback mechanism, right? We can imagine having one set of conditions that we try, we examine the results and the yield, and we use that to then revise the conditions and iterate. So I don't think it's necessarily true we have to get things perfect the first time. I think these systems can be made to be a little bit more robust and adaptive than that. But nevertheless, we are going to have, I think, this reality that many transformations won't give near quantitative yields. I mean, that's certainly for the way that we currently run reactions in the current transformations, there's no expectation that we get quantitative yield most of the time. And so for that, you're absolutely right again that we have to worry then about purifications. Purifications are an area where there hasn't been as much work developing models to design the conditions. For example, for liquid-liquid extraction, crystallization conditions, there's a lot of different processes that we can use for isolation and purification that are still rather challenging to predict. I think that's why you'll find that a lot of these sort of automated laboratory initiatives tends to focus on small scale synthesis where we can get away with chromatographic purification. And so while it's not, again, strictly universal technique, liquid chromatography is a fairly general purpose approach that can help us purify our compounds in many cases, if we're willing to invest the time into those separations.
Is the mic?
Okay, I hope this works. I have a question, especially on these generative models. I'm wondering how much of it is like empirical, or if they also include physical models. So, for example, you can calculate, let's say, binding coefficients through quantum mechanics, or have data on, speed, so kinetics. Is that also included in that, or is it purely empirical?
Yeah, that's a great question. I'd say that there's a range of approaches. In principle, so the generative models, I would think about them as a sampling approach, right? What they do is they help us propose new points from this vast chemical space, but those points in chemical space still need to be scored or evaluated or judged. And so the generative techniques are somewhat agnostic to how are their proposals going to be critiqued. And so people have used these where the evaluation uses sort of first principles models to estimate band gaps, for example, or trying to estimate transition state barriers or estimate other sorts of computable properties. I'd say in practice, many of us will use sort of empirical models to critique and score the proposals, but in other situations, you can absolutely plug in some more robust calculation to critique the models and steer them in that direction.
Thank you. The audience is happy. I have a question online coming from Zachary Crandall. It says, are you imagining a one-size-fits-all algorithm for this reaction prediction, or are you expecting specialized algorithms for different reaction applications? Maybe multiple phases of algorithms are another option too, one for retrosynthesis, then an optimization algorithm to run afterwards.
Yes, great question. So we do tend to have multiple different types of models and algorithms for each of these different tasks. Some of them are very related to each other. For example, you can imagine that a model that's designed for retrosynthesis at some level is just going from one molecule to another set of molecules, reactant molecules. Likewise, for prediction of products, if you just sort of invert the inputs and outputs, you can use the same kind of model, though it might be trained differently. And sort of folks like Philip Schwaller have done a lot of work in showing sort of one architecture applies in many different tasks. Now, certainly for things like reaction prediction or retrosynthesis versus optimization, those goals and requirements do look a bit different, and so those are typically decoupled. That's part of why when I typically describe ASCOS, it's sort of a software suite, right? It's this notion that we do have many different tasks and models that can come together to facilitate the workflows, where it's not going to, at least right now, it's not a single general purpose model that's making these recommendations, but rather a collection that are individually supporting different aspects of the decision. But there's actually a really interesting aspect of the question, which may or may not have been intentional, which is even if we think about reaction product prediction, right, which is sort of one task of taking starting materials, maybe conditions, and trying to anticipate the product, you could imagine a world in which we build one model that tries to cover all types of reactions and all types of substrates. But you could also imagine building a series of local models. So maybe one model is really good at Suzuki couplings, one model is really good at Buchwald-Hartwig animations. And so there are these different approaches that the field has seen, and in part reflects the way that we get our training data. So on one hand, a lot of the models that we build use literature data extracted from journal articles and from patents. So for this, the coverage of different types of reactions is immense. We have all sorts in there. We have the popular ones. We have a lot of very strange, unpopular reaction types that people haven't really done for many years. But then if we look at the data sets that come out of high throughput experimentation, those tend to be much more focused. And with those types of data sets, maybe they're doing one type of reaction, but they're varying substrates and conditions in a very dense way. And so we can use those to train models that are quite accurate within that domain, within that sort of input space, but don't generalize so well. And so maybe when we're then thinking about trying to predict products in general, if we encounter transformation that we haven't seen in a high throughput setting, we use our global model trained on literature. And maybe if we see one that does fit one of these more specialized expert models, we can use that instead. Again, these are different strategies that are still, I would say, complementary at this stage. We don't know which is the best one or if there is a best one.
Well, maybe in that same context, would you have a way of scoring your different algorithms? Is there some kind of benchmarking that you can do, or some other sort of objective measure that says this algorithm gave me a better result than the other?
Yeah, so we do try to have these objective quantitative benchmarks for the tasks that allow us to develop them. So I'll say for something like the prediction of a product of a chemical reaction, in principle, if everything is fully specified as far as the inputs and conditions, and your reaction is more or less deterministic at a macro scale, there is one correct answer. And we want to evaluate our model's ability to get that one correct answer. And so we can do that, and we can compare algorithms sort of head to head. Retrosynthesis is a little bit messier, right? Because retrosynthesis, sort of by nature, leads to many different solutions. And so if we look in one literature example and we see, okay, well, to make this product, here's the pathway that was used by some expert chemist that published in a very nice journal, we can say, I want my algorithm to recognize that that is an option, but I also want other options, right? I want to be able to see the full breadth of ways of making this compound. And for those suggestions that don't exactly match something we've seen before, we can't be positive that they'll work, right? We don't know exactly that they'll work. We have to find ways of evaluating their feasibility. And so this is actually quite a complex thing for the field, because there's some tasks where we have good quantitative metrics to optimize. We have these other tasks like retrosynthesis where there's legitimate ambiguity in what should the right answer be. And that's something that we're still grappling with.
Thank you, very clear. Let's see if there's other questions. Yes. Let's see if the microphone is working this time.
Okay, test. Perfect. So I have a second question. So all these databases, that sounds like an awful lot of data, to be honest. I was wondering if there are approaches for using big data techniques with all these chemical data, so like decentralizing computations, bringing the code to the data, and so on. For example, I find it hard to imagine like aggregation statistics with chemical data. For example, with ChatGPT, you can have word counts and things like that. And I was wondering if there already are like approaches in chemistry to summarize reactions to types or some labels, things like that.
Yeah, so I will say that this data is, the size of these data sets can be, the tens of millions of reactions, which is much larger than what, one lab is going to ever be able to produce. But at the same time, it isn't so large that we can't use sort of relatively, standard, consumer grade GPUs training these types of models. They don't take up that much space. They don't require as much of the engineering lift as some of these very large language models designed for very, very large scale training and inference. That said, I do think that this notion of distributed training is very relevant for the context of data sharing and data privacy, which comes up quite a lot in these conversations. So distributed training is not just for the computational expense purposes, but because the stewards or owners of a lot of these data sets are pharmaceutical and chemical companies who have a vested interest in ensuring that entries that contain proprietary scaffolds or structures that might lead to patented molecules, that might lead to blockbuster drugs, et cetera, remain protected enough to continue justifying that commercial investment into their development. So the opportunity, I think, exists for distributed, decentralized training with techniques like differential privacy and federated learning strategies. And we've seen a little bit of this in the drug discovery space when it comes to property prediction. There have been a few consortia, like the Melody Consortium in Europe is a great example, where they did this sort of pooled data, this sort of shared exercise of training models to understand how much better are models trained on everyone's sort of combined information through decentralized training versus trained on the public domain data. And they did see modest improvements in performance. We haven't had that analogy for chemical reactions yet. So I do think there are more opportunities to think about distributed training with the goals not just of decreasing cost or spreading out costs, but of ensuring privacy and IP protection.
Okay, thank you very much.
Thank you.
I think it was mentioned a little bit back that the main goal is also to predict either biological, physical, or chemical properties of these molecules. But right now, these algorithms, how precise are them? Or is it possible that some important properties of these molecules are overlooked?
Very important, or sorry, very, very likely that they're overlooked right now. So it's certainly the case that the type of property we're trying to predict and the way that we're trying to predict it has a large influence on the accuracy of it. So there's some properties that are relatively computable. For example, we can use density functional theory to calculate NMR shift, and so we can, with pretty good precision. And so we can also imagine having models trained to do that, where we have large amounts of training data, and we can build very accurate models for that prediction. But if we're trying to predict the in vivo response of some cell line to a particular therapeutic, then that's a task for which we're likely to have very little data. And so our ability to build an accurate model and to generalize is likely to be quite poor. So it's a little bit unsatisfying and trite to say that it depends very much on the task and the way it's trained, but it does. These AI tools, especially for property prediction, aren't silver bullets. They're not magic. They really just try to find these relationships between structure and function. And if that signal isn't strong enough in the data set, for whatever reason, we're not going to be able to generalize that well to new molecules, which is ultimately the goal, right? Discovering a new molecule means that we are generalizing beyond the molecules that we've seen before, because we're trying to find something new and something better.
I had a question actually that was more related to the effort that you mentioned at the end of your story, where you looked at the open source effort, where many different chemists are all contributing to a growing database. And I was wondering, in your experience, how well is that process happening? Because I think the chemistry field is not like, say, the astronomy field, where the astronomers all realize that at some point they need to build together the James Webb Telescope, otherwise they don't have such a beautiful instrument. Whereas the chemists might say, I'm just going to be in the lab on Friday afternoon, I do my thing, I invent something. I don't need this huge infrastructure, this huge effort, where everybody has to make some kind of contribution that is more towards the common good than maybe necessarily everybody's individual interest at that particular moment. So in your experience, how has that process worked out so far in the US?
That's a terrific question. And yeah, I'm glad that you've sort of raised the comparison to, I mean, astronomy. I think the incentives for data sharing in chemistry are not always present, or at least they're not external. And so when we talk to folks in the community about data sharing, I think everyone agrees about the benefits of such an effort. But I think there's also, of course, the costs associated just with, contributing to a structured data effort may take a little bit of extra time, especially the first time you do it. It might take a couple hours. Even if the next time you contribute data, it would only take, 30 minutes or so. There's still this sort of perceived barrier to this extra investments, where right now, again, the rewards are not as explicit or extrinsic. And so I think there's a lot of recognition and desire to have this take off, and some commitments from companies and some from particular like high throughput experimentation facilities and groups to contribute data. But I think more broadly, there's very much a cultural aspect, right, around the idea of data sharing and whose responsibility is it, and how much work is it, or should it be? So it's a tricky one.
Yeah, I can see that. The other thought I had, which might be difficult, is that suppose you have all the chemists all working on the Suzuki coupling reaction, and you would say, well, thank you very much, but we have done enough Suzuki couplings by now. We need to diversify a bit, and everybody should pick a couple of different reactions to contribute to the database. How would that work, you think?
Yeah, that's a terrific point. That's actually a use case that we've discussed is, part of what happens when you silo data is that, many different pharmaceutical companies have their own internal high throughput screen of Suzuki couplings to understand compatibility and conditions. And there's a lot of duplication of effort. And so one of the opportunities that I think with this sort of centralized infrastructure for data sharing would be this more explicit, in some ways, allocation or division of labor of, what is the field's collective knowledge of this type of reaction? Is it enough? Is there a spot where we're uncertain? Maybe there's a new type of ligand where we want to characterize its performance across a wide range of substrates. But then maybe we realize, well, our best investment of resources is in this other type of reaction. Let's try this new photocatalytic reaction instead, and that's where we should be investing some screening effort. So I think the sort of synchronization of data sets, this division of labor, deduplication of labor and results would be very beneficial, and that's the kind of thing that I think is nicely layered on top of the infrastructure that the ORD is providing here.
Thank you. Yeah, I can see that is going to be quite a big challenge for the field as a whole, I think, to get together and work this out in the right way. We are reaching almost 9 o'clock. I have one final question I wanted to ask you, which is not so much about chemistry and AI, but more a little bit about your short but very impressive career. And in a way, I was wondering, how did that come about? What sort of individual was important to you to sort of make the important career decisions that sort of helped you to establish yourself as a extremely successful professor at MIT in this rapidly developing field?
Yeah, absolutely. So I would say that I attribute a lot of my sort of success and ability to enter this space to the sort of mentors and collaborators that I had during my PhD. So I was very fortunate to work with two excellent advisors as a graduate student, so both Klaus Jensen and Bill Green, who are now my colleagues and I guess continued mentors in a different light. Because I found myself in an environment where I was given a lot of sort of flexibility to pursue sort of new-ish directions for our sort of local team, to try to understand new opportunities, to sort of form these new relationships. And I think having that sort of flexibility is really a privilege, I think, in a PhD position. But it also let us sort of form stronger ties with computer science colleagues like Regina Barzilay and Tommy Yakala, who I continue to collaborate with, and sort of more in an open-ended manner, explore the opportunities at the forefront of this space. And it was a little bit serendipitous, I think, that the opportunities in AI as it intersects with chemistry were really sort of reopening up, right? We've had AI in chemistry for a very long time, which I think some people aren't aware of, but we've had it for decades and decades and decades, and it's gone through these waves of utility and excitement. And certainly, I think we're in a renewed phase where there's a lot of interest and a lot of excitement, and I think it was very, very fortuitous timing, and a very good support network of advisors and professors who were willing to lend me some flexibility and freedom to pursue these ideas.
I think that is a great closing statement. Let's all thank Connor for a really entertaining hour. Connor, thank you so much.
Thank you very much.
For those of you watching, let's thank again Connor, but also next month we have Francesca Grisoni here live on stage, May the 9th at 8 p.m. And for everyone else who is here in the audience, let's join us for drinks. So thank you again, Connor. Bye-bye.
Terrific. Cheers.